Okay, so thank you, everybody, for tuning in today, for joining this next session, complex webinar. This is one of the topics we've actually already covered once this year. So this talk is on parallel computing concepts. Earlier in the year, I think in January, Bob Sinkovitz, who is the PI of the complex project here, put together this material and presented then. So this is my take on his slides. And I think maybe one thing to note, Cindy and Nicole, is I think the PDF here is saved in a not quite the right format for the screen. So I think there's a white bar at the bottom you might see. So maybe we should fix that in the future. But yeah, as Cindy mentioned, I'm Marty Kandes. I work in the HPC User Services Group. So if you happen to be working on any of the supercomputers or HPC resources we have at SDSC, and you have an issue with getting your code up and running, or questions about how to get access to time on the supercomputers, we're the team that you'll generally eventually your email will show up in our inbox, and we'll help you out with any problems that you have. But as of course, as part of that, our role in that team, we do a lot of user education. And so sometimes, we put together the proposals on new projects of how to sort of redesign our educational material for people who want to use our computational resources. And so this complex project is one of those new education programs funded by NSF in the last year. And so the idea of the complex project is to teach end users how to use high performance computing resources. But for those who may not be active sort of developers or not have sort of, you're not writing your own code. You're usually, using someone else's code, and you just need to understand enough of the core concepts of parallel computing, bash scripting, security to interact with these advanced sort of cyber infrastructure resources and get your research done. And so that's sort of the idea of the complex project. So we're trying to sort of reformat a lot of the material that we've had in the past for this sort of end user base. So hopefully, if you're here today, you fit into sort of that broad umbrella of users, and that's sort of the level of material and sort of in depth of the material that we'll cover in any given topic. It's sort of the intro to where you need to start in any given topics that are part of the complex program. So today, what we're going to cover is the parallel computing concepts, and we'll start off talking about what is a process, what is a thread, and how that relates to two types of technologies you'll see mentioned in any sort of parallel application you might be dealing with MPI and OpenMP. Then we'll talk about a little bit about how MPI and OpenMP are used within applications and how those applications can be sort of broken apart and run on different computational resources and sort of hybrid applications that might use both of these programming paradigms. And then we'll talk about some of the limits of parallel computing, which is the limits are effectively set by what's known as Amdahl's law. And so we'll explain what Amdahl's law is and how it relates to, any applications that you might be using, and how to, remember that this is a sort of a fundamental limit on any application you're using. And so it gives you some sense to think about, where you're going to get the most performance out of any given application and how to set your requests for resources on supercomputers in the future. And then there's sort of a bunch of ancillary topics that we'll touch on at the end of the talk. But that's sort of the core structure of today's material. So again, today is sort of the opening talk for Complex that we started with this year. And it's really, the idea is hopefully you're here because you've been working on your research, say on your laptop or maybe a desktop system in your research lab, and now you really need to use larger, more advanced computational resources where you're really going to take advantage of an application that is able to harness the concept of parallel computing, right? And so this is kind of with the assumption of the talk. It's like if you've never taken your application you've been running locally on your laptop and taken it to a supercomputer and you can see resources, and it is parallelizable, how to get started with sort of the terminology and the different concepts that you might run into. And so I might have kind of summarized that here, but this is sort of the Bob's who this session is intended for. So yeah, anyone thinking about running applications on parallel computers who want to, understand how to request time on campus clusters or national computational resources like we have at SDSC. Of course, if you're making purchasing decisions on computational resources for your lab, understanding some of the concepts of what you need to run the types of applications you want in your research lab, that might be also helpful. And then, of course, anyone simply curious about parallel computing and getting started. So yeah, this is the motivation here of this talk is, again, in the complex framework, trying to bring the concepts of parallel computing that the people who are writing parallel programs themselves need to know, but to focus on introducing those concepts to people who don't necessarily need to write their own parallel programs, but need to understand maybe how to run a parallel program that exists in your research community. And so that's the motivation here. Can we convey sort of those key concepts for you who might be using a parallel program or want to use a parallel program and run it on, some of these advanced resources? So there's 3 myths in this talk about parallel computing. And so the first myth is just that, parallel computing is only for sort of the hard sciences, physics, engineering, weather simulation, these really intensive computational, traditional simulation type workloads that have been carried out in the past. But, today we have researchers from all different fields using parallel computing in many ways. And I mean, the most obvious is if there's AI or deep learning involved in your research field today, that's sort of, parallel computing is intimately intertwined into, all of the AI and deep learning type of applications that are being used across all sorts of fields today. So that's myth number 1. Myth number 2, which is very important, I would say probably the most important one maybe of the 3 here, is, simply adding more computational resources to your problem does not mean that it will make your problem get solved faster. And there's a few different ways to look at this. The way that's probably most immediately obvious when we get users on the systems for the first times and they're running their first parallel applications is, if an application wasn't written to take advantage of multiple CPU cores or GPUs or other types of computational resources, just requesting that the supercomputer give you time on one of those resources or number of resources doesn't mean the code will automatically run faster, right? It has to be designed to run on specific type of hardware in the way that it wants to get, in the ways that can be parallelized across multiple resources or advanced resources like GPUs, right? So if the code that you're using, the application you're using, doesn't have somewhere in the documentation that it can take advantage of multiple cores, you don't want to request a whole compute node on a supercomputer to run that code because it's not going to take advantage of that hardware, right? So you really do need to understand at least the basic strategies used in the code to parallelize the workload of that application and match it to the appropriate hardware that you want to use, right? So that's definitely, you know, something we see very, very often of just that either the application that someone's trying to run doesn't take advantage of multiple, say, CPU cores or GPUs, or they simply haven't sort of given the right sort of, you know, input parameters and things to, you know, tell the application, I want you to utilize all of the resources that I've requested from this supercomputer. So that's definitely, I would say, for me, the most important one to remember, that you really need to understand at least how your application is parallelized, and then understand how to ask it to utilize the multiple cores or the GPUs that you want on the systems that you're running it on these HPC systems. And myth 3 is kind of, I think, the obvious one from this talk is you don't have to be a programmer to utilize parallel applications. You know, you need to learn the basics that are hopefully taught in this section, that there's something called processes and threads and something called MPI and OpenMP, and a lot of applications are written with these parallel computing concepts. And once you understand how to, run these types of applications on HPC systems, you know, it'll apply to many types of applications, right? Not just maybe the one that you're interested in today. So, yeah, I think as I've sort of already mentioned, in many cases, you know, researchers in many different fields are not necessarily writing their own applications anymore. They're using sort of, you know, well-established community projects that exist. You know, these are some of, you know, listed here are some of the most, definitely some of the most common ones that we've seen in use in the past on our systems. WRF is like a weather simulation model. Amber is a molecular dynamics application that we have some people at SDSC that work on directly. RAXML is a phylogenetics code, so trying to understand the history and structure of evolution in certain type of species, and then, you know, sort of the traditional physics simulations for understanding electronic structure in materials. And this CP2K application example here. But in all the cases, there are developers, and actually pretty big developer base out of someone's research lab or multiple labs that work on these types of large applications that at the end of the day, you know, most of the people, you know, running simulations with these codes aren't the developers. They're, you know, the end users. They're sort of the chemist in the lab who wants to sort of try to understand their material properties through an electronic structure calculation. You know, they're not the ones who understand the methods necessarily that underlie the calculations themselves, but can sort of recreate the experiment in, you know, in the computer, basically, to understand what they see in the lab, right? So that's sort of where we're coming at with this sort of perspective on who's using these community codes and, well, why they need to understand some of these concepts. So one thing that's new to people who haven't worked on an HPC resources and supercomputer before is sort of trying to conceptualize the structure of all of the components that are, and language that describes what they are. You know, it's very different than you're working on your laptop with a single processor, maybe with a few cores. There's a lot of other components that go into these systems. But at the end of the day, you know, you start out sort of, you know, every compute node is kind of like your, you know, self-contained, you know, computational resources that makes up any of these supercomputers. You know, has usually multiple processors. Each processor has a computation, you know, some set number of computational cores. For example, this diagram is for expanse on one type of compute node. You know, we have two processors, which are, you know, two sockets, sometimes referred to, on each compute node, and each processor has 60 compute cores on each processor. So each node has 128 CPU cores per node, right? And then, the physical design of the systems and the vendors, so here in our case, we have 4 nodes that are loaded into things called chassis that aren't usually too important for end users to know. And then, each of these, chassis are then racked into these different racks and spans at SDSC, which this is an example of, is multiple racks that are then networked together with high speed or low latency, high bandwidth type networking. In this case, there's InfiniBands, which we won't talk too much about the networking today, but there's always, and there's specialized file systems for different reasons, and so there's a lot more going on than would experience with your laptop or desktop. And so learning what all these pieces are and how to use them over time is important, because at the end of the day, these are also shared systems where you are in a community of users who are trying to use the system at the same time. And for different reasons, you can actually bump into other people and cause problems for their jobs that they're running, or vice versa. And so there's sort of an etiquette to working on these systems as well, but it's sort of beyond this stuff. But learning the lingo of how to describe the different components and what is important, because at the end of the day, you're also going to eventually want to request, like, I want 2 nodes from this set of node type, that has maybe GPUs, or the one that doesn't have GPUs, right? So you need to sort of just understand sort of some of the hardware architecture and the structure of how these systems are set up. Okay, so moving on. So it's sort of the background material. When you get started though with parallel computing, probably the most important concepts to understand and sort of segment out and sort of understand somewhat deeply, at some sort of practical level at some point, is what's the difference between processes and threads. And so a process is what the operating system sees as an instance of your application, your program that's running, right? So it has a set of resources are assigned to that process, right? So when you start up your application and execute it, right, a process is spun out, and that's what's sort of shepherding your calculation and all of the things that it's doing, right? It has it controls how much memory, or not necessarily control, but there's always some memory associated with your application running, some sort of IO descriptors that allow you to write files or read files, open them and close them, and how many computational cores or GPUs are associated with that process, right? There's all of the sort of resources that you might want to use are sort of associated with the process that's running your application, right? Or processes in the case of parallel, right? Threads, on the other hand, are sort of a more lightweight part of application's execution, right? You can kind of assume that in an application that's running, it might spawn what's multiple threads. And so your application is running in a process, but that process might also be overseeing the multiple threads that are spawned by that application. And so in the case of a parallel application, you might have just an application that is running in a single process, but that process might be allowed to run on multiple CPU cores. And so you might only spawn threads to fill the computational work across those cores inside the machine, right? And so the key thing to remember about threads is that they run inside of processes, and right, because of that, they all have access to the memory that's associated with that process, right? So this is what's known as a shared memory model, right? So threads are usually associated with a shared memory model where each process has its own memory. And so if you have multiple processes while you're running your application, what we're talking about, that's what's known as sort of a distributed memory model. And so anyway, these concepts are very important, and we'll show some diagrams later of sort of how this looks in a sort of block diagram way of how processes and threads interact with the CPU cores on the system, things like that. But very, very important concepts to know if you're not familiar with them. Okay, so this might just summarize things I've already said, but yeah, so processes are a little bit more incur a little bit more overhead because they have their own sort of memory space and other resources that they have to sort of manage, and it's sort of a higher level object in the operating system that's managing your work. And while threads are sort of below processes, they're sort of spun out of processes that sort of can do independent types of actions across maybe multiple cores that you have associated with your application or your application running across, but they're all running within a process in this sort of shared memory space. Yeah, I might have also already said some of this, but so yeah, so why do you care? Yeah, so again, when you are using another application and you want to run it on an HPC system, right? You need to understand like what parallel programming model has it used? Is it using a distributed memory model where it's spinning up many processes and multiple instances of the program to get the work done? Is it using a single process, but then spawning multiple threads in the application, the sort of shared memory type of space? And one of the key things that maybe I didn't mention there is, the distributed memory applications, right, allows you to run across multiple nodes. So if the application you're using says it can run across multiple nodes in an HPC system, right, it's using some sort of distributed memory model. Whereas a threaded only application, right, it is limited to that shared memory space, right? So you can only run on a single compute node. So if the application that you want to run is only using a shared memory model, you'll never want to request more than a single node, effectively, from in your jobs that get submitted to the HPC resources, to the schedulers that manage those jobs at those levels. Of course, there's another case that we'll talk about here is, right, many applications use a hybrid approach where whatever programming method that they're using or framework that they're using underneath, it might be a hybrid of using both distributed memory and shared memory. And so you both will have your application maybe have multiple distributed processes across multiple nodes, and then on each node, each process might be spawning, multiple threads within each process, right? So that's sort of a very common thing that you'll see for many applications, right, that have been developed over years and years. Because if this sort of distributed and shared memory model and hybrid application sort of approach has, been around for at least 30 years almost now, or if not longer.
Hey, Marty, we have a question.
Yes.
That I wanted to. So the question is, while on the topic of processes and threads, could you discuss the idea of task? Slurm is a task-based scheduler, but how does a task map into process thread discussion?
Sure, that's a good question. So yeah, I'll try to answer that quickly. I think maybe Trevor Cooper is here, who is our Slurm guru. He might have a nice longer answer for you, but to keep it short, since we want to keep on time here, is effectively the number of tasks that you request usually are in, say, what we'll talk about here shortly, for like an MPI application. Usually you want to set that task number to the number of MPI processes that you want to run on the system. So that number of tasks, really usually maps directly to the number of processes you want to start, right? Because there's always another flag usually that I recommend is you request the number of tasks, say, per node that you want, and then you request the number of CPUs per task. right? So that number of CPUs per task usually sets the number of threads that you'll want to spin out in every process, right? So there's probably other ways to think about what, Slurm says is a task, but in the most common cases, usually the task corresponds to processes, usually MPI processes, and usually the number of CPUs you assign to each task in the simplest cases, right, are what you'll spin out that number of threads as well. So yeah. So hopefully that helps. And I'm sure Trevor, if he has anything to add, he'll point you to some other parts in the Slurm documentation if you're interested. Yeah. So yeah, let me, so there's one more question. Can you correlate a task with a Linux process? Yeah, so that's a little bit into the weeds, Homer, but yes, I mean, you will see if your processes, well, yeah, I think the question is relating to Slurm tasks and Linux processes. I'm sure you can link them at some point, but yeah, I don't, but yeah, you can definitely see your processes running the top. Anyway, so that's kind of into the weeds. So let me go ahead back to the higher level concepts here. So with that discussion of processes and threads, right? So the most common distributed memory parallel programming framework that you're going to run into with any application is MPI. So this is the message passing interface. It was sort of, I think, developed in mid to late 90s, the first sort of standard MPI. And so what this allows you to do is do this parallel or sorry, distributed parallel memory model where you can, have the processes talk to each other by explicitly basically passing data between processes, right? And so this is, sort of the de facto standard for writing distributed memory parallel applications. And so there's different implementations that you'll see. Of course, I think as also just the back a second, right? This is for C, C++, and Fortran. A lot of other applications that have higher level sort of frameworks that they use, like Python and things like that, a lot of them still link to, or even MATLAB link to lower level libraries of C, C++, and Fortran. So even though your application might look like it's a mostly Python application, or even if you're using something like MATLAB, right? There is Fortran code or C code probably beneath it somewhere. And maybe there's an MPI interface as well that will allow you to adjust the number of parallel processes that application starts. And, but there are different implementations of MPI libraries. There's OpenMPI and Bapich are sort of the two most popular open source one, and MPitch is another we don't use too much ourselves. And even, specific vendors have their own, like Intel and Cray and things like that. So you'll run into different variants of MPI, and every implementation that you might use to compile your application, or that an HPC center might have already compiled and placed on the system for you. For whatever reason, they might use a particular type of MPI. It's just there's different flavors out there, but they're all sort of, there is a standard that each implementation is in various states of meeting those standards. Essentially, that everyone has agreed that this is what an MPI library should do. So there's other distributed memory parallelization libraries out there. So you might run into other types of frameworks. I think I did see maybe Johnny was on the call earlier, who he has in the past worked with a Charm++ application. So this is sort of a non-MPI application that uses this other sort of distributed memory parallel programming framework. So there are others out there, but they're just not as popular. Let's skip this slide. And And so, yeah, so this is, I think this next example here is just to show you sort of what an MPI application looks like and sort of, just to reiterate that it's low level C or Fortran code, and it makes things a little bit more complicated, right? For the application developer, again, you don't necessarily, as someone who might not be developing an application, you don't necessarily need to know these details, but things get more complicated when you have to explicitly start passing data around from one process to another, from one sort of memory buffer to another, and there are bugs in MPI code, so the things like that you might run into as an application user. But this is what a hello world in C looks like without parallelizing it. If you wanted to run a hello world and print that from many processes, this is what it looks like, right? So there's some sort of set of MPI commands in any given framework that you need to initialize the communication process and sort of understand what application is labeled with what sort of rank or numbers, what they call sort of an ID number. And so you can pass data to and from and know what rank your process is in the sort of global sort of communication layer that's set up from the initialization. So it's not too important to look at the details here, but just that things get more complicated when you start talking about distributed memory programming. On the other hand, we talked about threads, and what I would say is simpler than MPI for sure. If you want to get involved in sort of learning a little bit of parallel programming, OpenMP is where you would want to start if you know C, C++, or Fortran. It's a compiler directive based parallelization library, and which means that if you're writing your code and you basically sort of decorate pieces of your code, I think the example will show shortly, with some special directives that tell like to parallelize a loop or spawn two threads, have one thread do this and one thread do that. It's a way to much more easily sort of start understanding parallel programming if you want to get started there. But at the end of the day, it's, again, this is the most popular shared memory parallel computing sort of framework to get started with. So this is a lot of different code out there has been written with OpenMPI in mind. Even the latest standards of OpenMP even support offloading to things like GPUs, and so it's not just about multi-threaded programming on CPUs anymore. It supports GPUs to some extent, and yeah, so it's the most popular one that you'll run into. There's other types of threaded programming models you run into, like pthreads is kind of the older one that you might run into with some applications, but essentially OpenMP is basically built on top of pthreads, so it's OpenMP is like the easier way to use pthreads, but if your application was written with pthreads directly, so these are the types of things that you might run into with shared memory applications or with hybrid applications that use both MPI and OpenMP or some of these other shared memory. And yeah, so again, just as a personal recommendation, if you do want to get into understanding some parallel programming, know a little bit of C or C++, Fortran, OpenMP is where you would want to start. But if this is just a simple programming that looks like it's adding two vectors together, so you have A and B, and then they want to parallelize, I think, that last loop C. And so this is what OpenMP looks like. This is a serial program here. And basically you just add in, mostly, this sort of incantation, this directive that tells, your OpenMP compatible compiler to, parallelize this loop for you, because the adding each individual element is a trivial problem to do independently, and so you can spawn multiple threads and getting multiple numbers in that vector added together at the same time if you have access to, say, multiple compute cores in your process. Okay, so that's OpenMP. Yeah, so this is kind of the big picture slide, I guess, that MPI is about managing processes, this distributed memory model. There's different flavors that you'll run into that are shown there in the each color. And then on the thread side, you know, the multi-threading shared memory model, if your application uses that, you'll most likely run into OpenMP and the different compilers. And again, this is a compiler-driven type of parallelization where so the compiler has to support OpenMP. And it's usually just a flag, like if you have an OpenMP code and you compile it, you turn that flag on and just compile things like normally you would serially. And it'll understand all the directives and set things up properly. Right? So all the major compilers support OpenMP, whereas MPI is a separate library that needs to get linked in and you kind of compile. If you are in the case where you have to compile something yourself. Okay, so now we're doing time about 20 minutes left for the main talk. So hybrid applications. So I think as I've hopefully made clear, this is usually when you have applications that use MPI and OpenMP together. And yeah, so I would say we're seeing more need to, some applications you can run with MPI and OpenMP. And in the past, sometimes when these hybrid applications, when we would build them and test them for our systems, sometimes it was advantageous to just say turn off the OpenMP, like only compile it with the distributed memory MPI library, right? Because there wasn't really much of an advantage to hybridizing any of the calculations that we would test. And so it would actually be more performant to not use the threading within each process, right? But I think as time has gone on, and now there's more CPU cores per processor and only increasing, and sort of the actual physical structure and architecture of the CPU processors has gotten more complex over time, right? So I guess one of the takeaways I wanted to emphasize in this talk is with the density of computing cores being added to any given individual processor, the only way forward for the most part for new applications is to go parallel, right? So even though there's a lot of, this has been going on for a very long time with certain applications, if you have an application that you're working on and you're not thinking about parallelizing it in the future, or your group isn't, definitely, have a serious think about that, because at the end of the day, the computing power in the future only is going to come, for the most part, from parallelization, and that's sort of just due to the physical limits of the technology that we foresee so far in the future. And so it's an important point, more for people who are developing their own applications. But if you do get interested in learning how to do that, it's definitely worthwhile. I would say. Anyway, yeah, so I think this kind of the point here for hybrid applications is why hybridize? Well, it's like if you only write it in OpenMP first, your application, or if someone writes their application OpenMP, okay, they're limited to a single node. The interesting thing today is that why we're seeing hybridization come back is important in terms of actually when you run the code, is that each individual compute node itself now on some of these HPC systems look like they have little nodes of cores on each processor. And so using MPI placed in these sort of complex architectures with the threading turned back on is actually helpful. And so it's, going this hybrid approach is sort of useful again, I would say, from what we see in practice for most applications of having both the distributed memory model in use and the threading of each application in use as well. So yeah, the next few slides will sort of hopefully give you some visual context of what we're talking about when we're talking about laying out processes and threads on compute nodes in an HPC system. And so the example here is a 2-node system. So you have, one processor on each node essentially, and each processor has 16 CPU cores where the instructions are each executed, right? So if you have 16 things to do on each node, you can get 16 different things done. If you have a core for each one to do it in parallel. And then you have some sort of network in between that allows you to communicate between the nodes if you have, say, a distributed memory application. So yeah, this is the example of a message passing only application. So if you have a message passing only application and you request these 2 nodes, you can assign, typically what you would do is assign each each MPI processor to a single CPU core, right? So in this case, you would have a job with 32 processes start up across the 2 nodes with 16 processes per node, because those are going to get mapped directly to each individual core, right? Typically, you only want a single process and a single thread running on any individual compute core. Sometimes there's advantages to other things that we won't talk about, where you have multiple processes or threads running on a single core, but in general, you don't. So that's sort of a very straightforward, typical mapping. If your application is only MPI and you start up the job on 2 nodes, each node has 16 cores, you'll start 32 processes across all. Each process will fill a single CPU. At the other extreme is if your application is only a shared memory threaded application, right? You will only be able to use a single node. And so you effectively, when you run your application, you will have a single process start, and each thread will be assigned to each individual CPU core within that process, right? And so that's the sort of other extreme, where you have one processor and 16 threads, right? Within that single process, running across the different CPU cores you have access to. And this is sort of what a hybrid application might look like across those 2 nodes. So if you have an application that has both MPI and OpenMP, you would have, in this case, what we have is 2 processes per node with 8 cores assigned per process. And so you can have 8 threads on each of the, for one thread on each of those cores. So you have 8 threads per process on any given sort of, while the application is executing, right? And so you have options in this hybrid case of how you want to lay out the processes and the threads and map them to the cores, right? So this is one of the most important things that if you're starting out with an application that you'll want to, if it's a hybrid application like this, you'll want to understand like what is sort of the sweet spot of the number of processes and threads to the number of cores on the system that you're running, and how to lay out that sort of hybridization strategy for the application, right? Because every application will be slightly different of what that looks like for any given HPC system and node architecture you might be running on. It's not always going to be the same. So anytime you go to a new computer and have a new type of node architecture, don't just use your job script from the last supercomputer and just assume it's going to work perfectly and be the most efficient on the new system, right? Because the architecture of the processors and how many processors per node and cores matters to the application, right? And how and why that is, I think, is in the next few slides. Well, yeah, so these slides are just showing different ways to lay it out in those, but I think, I guess maybe it's a little bit further along. But the main reason, for understanding like which of these layouts is the most useful for your application is because, one of these will be the most efficient for your given problem for that application, right? And so trying to understand, how to lay out the processes and threads on the system you have access to for your application is, the hard job that you have as an end user of the application. Right? So that's kind of the most important. So to make sure that you're using the resources efficiently, you need to understand which of these pictures for your application would make the most sense, right? And the only way to really do that is to experiment, right? Because if, you can ask people like us, but if we don't know the application and we haven't tested it a lot ourselves, we probably don't know either. So this is kind of where you getting familiar with these concepts and understanding how to sort out that question is the most useful for not only yourself but for us as well, because we probably don't have necessarily for your application the experience to tell you which one is probably the most likely. I mean, we can help you get started, but it's really an experimental question in most cases. Okay, so we have about 10 minutes left, and probably the most important sort of high-level concept is Amdahl's law, because it will inform you, I think, in terms of that problem of trying to understand how well your application can scale and fit within, which version of those processes and threads layouts makes the most sense for your application on a given system, is always going to run up against Amdahl's law and how scalable the application you're using is for the problems that you have. And Amdahl's law is pretty simple, actually. If the Wikipedia page is nice, there's a lot more detail and history, I think. But essentially what it says is that the speed up your application can attain on any given computer is proportional to the serial fraction of code that must run, right? So every application, no matter what you do, there's going to be a section where it has some serial execution on a single core. No matter if you requested 100,000 cores, there's probably a very small part, at least at the beginning or at the end, where there's some, or maybe some small parts in the middle, where there's a serial bottleneck that you run into where you just have to wait. Everything has to stop and wait, resync, and maybe write a file or whatever. Most applications have some sort of point where they have to stop, do something sequentially, and then restart all the parallelization, right? And so this is very common, but it's that fraction of time that your code has to execute sequentially is what limits the fundamental maximum speed up you can get. And that's what Amdahl's law says. And so, yeah, you know some math, you just do like the limit there. Yeah, so 1 over the maximum speed up is 1 over the serial fraction of the code, essentially. And this is what this looks like, plotting that function up, right? And so if your code is only 50% parallelized, so if the application you use only takes advantage of parallel computing concepts like distributed and shared memory programming, if only it's only running half of the time in parallel, the maximum it'll ever run, despite however many cores, GPUs you throw at it, right? The maximum speed up will be 2, right? So you don't want to request 1,000 cores if you can't run on 1,000 cores, right? So there's a fundamental limit for any given application of how fast it can go. So this is where that issue of you experimenting with the code that you're using in the application and how it runs on any given system, comes into play, right? Because if if it's an application that was developed by someone in your lab and you just need to run it, we're not going to know what parallel fraction is, and probably no one does. Someone has to actually go investigate that, but you can experiment and see how fast sort of the speed up is looking as you experiment with some scalability and get a sense of like where is going to be the sweet spot of how parallel we can solve these problems with any given application, right? And I think next slide, this is kind of maybe where it gets, where maybe the wow moment. Maybe it's like this is as I mentioned, sort of the fundamental problem with sort of where computing is going, right? Where, you know, it's been going for a while, where, you know, the only thing we can really do is pack more computational cores and processors into smaller packages, right? The speed up is all from, majority is coming from parallelization these days. But this, you know, Amdahl's law here, right, says that even if your code runs in parallel perfectly, 90%, 99% of the time, your maximum speed up is, you know, what, 100, right? So you're never gonna be able to use, like on Expanse, each compute node has 128 cores. And so if your code isn't 99.5% parallelized, you know, you probably don't need more than a single compute node on Expanse for any job that you run, right? And so, you know, if, you know, hopefully if you're using a large community code, there's some information out there, scalability and the ability of codes to run on problems in parallel. You know, hopefully that's sort of documented in some of these larger codes. But if you're using sort of a code from a smaller community that doesn't necessarily understand the scalability of the code, or if it's just out of your own research lab, you know, this is something to keep in mind, right? That, you know, if you start trying to scale beyond what the theoretical limits say, you're just wasting compute time, essentially. Okay, so that's definitely, again, one of the most important takeaways from today. So I think, you know, we have a couple minutes left, and, you know, I'll just say now, I'll probably just run through these last bits pretty quickly. You know, we do stick around for about 30 minutes after the end of each first hour session and just answer questions, and we can talk more about the concept. So if I, you know, breeze through anything on the next couple of slides that you want to talk about more, let's definitely do that. But I think those, you know, we've covered the key concepts of, you know, processes and threads, what MPI and OpenMP are and how they relate to them. And then the most important part of this, you know, topic is, you know, Amdahl's law. It's like, if you are using an application, there are real limits to how fast it will go on any system. And before I maybe breeze through the rest of the slides here is, you know, one of the interesting things that we get sometimes, not too often, but you know, an end user will be, you know, taking their application that they're developing for the first time, you know, that they've been developing on their laptop or their, you know, personal computer at home, and then they bring it to a system like Expanse, and we start running it, and then we get the question, it's like, why is my application running slower in my testing on Expanse than it is on my laptop at home? And the problem there is, like, they're usually running some small test calculations, like maybe a few cores, maybe, you know, or even maybe their code is, like, you know, single threaded, so it only runs on a single core. And the issue there is, you know, I mean, large systems like Expanse and other supercomputers you run into, right? I mean, these are long-lived systems that, you know, we purchased the equipment for Expanse back in 2019. So you have 2020 roughly technology that you're running on, you know, those compute cores are from 2020, whereas your laptop might be from 2024. And so your single individual core or a few cores that you have in your laptop are faster than the supercomputer. You know, so, you know, trying to figure out, you know, when do you actually need to take your research code on your or application that runs perfectly fine on, you know, the compute resources you have access to that might be newer and might be more performant than an HPC system is also another, you know, thing that comes up from time to time. But anyway, that's just kind of a side note. So I think, yeah, so we've sort of talked about the, you know, Amdahl's law and this upper limit of scalability for any application. And the reasons for that are, you know, these are the typical three that limit that ability to parallelize and given code. You know, it could be limited by sort of the memory size per process, the amount of communication time that has to happen to, you know, pass data between processes, or if you if you are doing a threaded application where different threads do different types of tasks, right? The compute load for each given task might be different. And so you have sort of a different amount of computational work that gets done on any given process or in any given set of threads. And so again, at some point, usually the problem is you have to synchronize the data and, write output file or do some other action where everybody needs to know what's happened on the different processes and the different threads. And so this synchronization process, for these different types of problems just naturally has to happen. And yeah, I think maybe we'll skip that. Let's get a little bit fast, but basically the idea here is like, yes, it's, this is sort of an illustration of Amdahl's law with Hello Kitty. That's what Bob is going for here, where essentially you have, you have the task of, say, painting a fence. It's obviously easier to get it done faster if you have 2 people. And maybe if you have 4 people, and maybe if you have 8 people, it starts getting a little crowded and no one has enough room to paint or not. There's just not enough work at some point, right? And you sort of, there's too much overhead. Too many people are talking and bumping into each other, and, painting a small part of the fence. That's kind of the analogy here. It's sort of similar if you put, maybe this is another good point to make is like if you're getting started with understanding processes and threads, one of the most common problems we see is end users not matching the number of processes and threads that they can start on the computational, the CPU cores that they want to run on, right? So in general, there's got to be a one-to-one sort of mapping at some level there. Usually you don't want to spin up multiple processes per core, multiple threads per core. That's just sort of the general rule. But if you're getting bad performance, you might be accidentally starting extra processes or threads on a given CPU core, right? Or some set of cores, right? And so that, is definitely this congestion of trying to do too many things in the space that you have is a common sort of issue we see when people first get started. And so I'm gonna sort of skip through this, but you can, again, Bob has an earlier recording where I think he got to most of this material. So he has probably some other nuggets that would be helpful about load balancing and things like that. But the slides are pretty good at explaining what he's talking about. And so let me see if there's anything else I want to, communications overhead, and gives kind of an example here. I think that's about it for the top. Yeah, I think maybe one other thing to note before we end this session is, in addition to Amdahl's law, there is something called Gustafson's law. And so this is sort of the natural thing that happens when your code or application that you're using sort of reaches its scalability limits. The way that you can get more scale, and what usually happens with these applications is, even though the code has sort of a fundamental upper limit and speed up, it doesn't usually have an upper limit in terms of the size of the problem it could solve if there's a bigger computer. And so what happens is, even though there's, for a given problem size, Amdahl's law is true, where if you try to throw more and more computational resources at the same size of problem, it will not scale. It'll reach its maximum. However, if you scale the size of your problem to the computational resources you have, it can keep going. So it's just another thing to note and keep in the back of your mind that, even though for a given problem size, Amdahl's law is true, if the problem size changes, you can keep sort of solving larger and larger or more dense, higher fidelity problems if it's like a simulation code or things like that. So just another thing to keep in mind when you're thinking about how does your parallel application work and what are the real limits for solving the types of problems that you have. Okay. And I think I'm just going to go to the And here, so yeah, please, if you're, interested in this topic, there's some nice other notes about, how to display scaling results at the end here and where you should be on the scaling curve. But, there's, again, a host of resources out there about this type of topic when you're getting interested in parallel computing. And this talk is really just about some of the core concepts that you need to start understanding, and, the terminology that relates to running parallel applications on HPC systems and supercomputers that you might be interacting with. So with that, I'm about 5 minutes over, and I will stop there. So we can stop the recording, Cindy, and stick around and ask any questions for the next 25 minutes or so.